Hey folks, I'm going to briefly go over the most missed questions on the chapter 29 and 30 test. The 5 questions listed here, number 9, 10, 16, 22, and 25 were the most missed. Um, and all but 16 were about half and half. So 9 and 10 and 22 and 25 was about half people got it right. 16, only a few folks got it right, and I think I know why. All right, so I'll start with number 9. Okay. And I got the test up here. I'm doing a preview of it. So for number 9, they give you a charge, Q. They give you a velocity. It's in 3 dimensions. And they give you a magnetic force acting on this. And they ask, and they say the X component of the magnetic field is 0. Determine the magnitude of the Z component of the magnetic field. Okay. So basically you're doing cross product. So force equals QV cross B. Okay. And because it's like 3 dimensions, it's probably good to use the whole matrix thing, right? So what I did is I wrote force equals Q. Now for me, the charge was 3, I believe. Yeah, but I'll leave it as Q for now. So Q, and then we're going to do that whole matrix thing. So we're going to do our I, our J, our K, V, which for me was 5 and 8 and 6. And then B, we don't know. But they did say the X component of the magnetic field 0. So I'll put a 0 for that. And I'll call this Y and Z for these 2 unknown things. So that's your V and that's your B. Okay. So our force equals Q times, okay. The I hat component would be J cross K, okay, which would be, this is our little thing here. So J cross K would be 8 and a 6 and a Y and a Z, and that would be I hat, minus, all right. The J hat is I cross K, which is negative J, that's why our negative sign's sitting there. And here you get 5 and 6 and 0 and Z, okay, and then we got plus, and then, oh, that's J, sorry. And then our K hat is I cross J, which is 5 and 8 and 0 and Y, and that would be our K hat, okay. Boom. All right, so the only one I'm going to focus on, I'm trying to figure this out, right here, Z. I'm just going to focus on just the J component because, like, the only unknown there will be Z. So the force in the J direction, so for me, the force in the J direction was negative 38. Okay, now everybody's going to have different numbers there, but I had negative 38. So I know that negative 38 equals Q times, okay, and so here is my I'm just looking at this because I'm only focused on the J component because that's going to get my unknown there. So I've got negative, all right, 5 times Z minus 0 times 6, so that's just 0. Okay, so I get negative 38 equals negative, I'll put the negative there. Q for me was 3, and then times 5, and then times Z. So basically my Z component of the magnetic field will be, the negatives drop out, it'd be 38 over 15, which when I did that in my calculator, I got 2.53 repeating, let's see, magnetic field would be Teslas. Okay, so that should be the answer to number 9 for me. Okay, so again, cross product, you got to do your, I mean, you don't have to do the matrix thing. You kind of just figure it out here, but I wrote it out just to kind of, what it would look like if I did the whole thing. All right. By the way, number 9, 31 of you got this right. So half of you got this right. So that's pretty good, actually. I'm pretty happy with that. Let's see, number 10. Okay. 32 of us got that right. Let me put that up here really quick. So number 10. They give you a length of wire with a current, and they give you a magnetic field that has 2 components, an I and a J. Now, they do say the current is in the I direction, the X direction, okay? Remember, and I think this is probably what most people missed here. So we're going to use force equals IL cross B, okay? This is in the I direction. So for the magnetic field, which has two components here, in this case an I and a J, I'm only going to focus on the J component because the I component isn't going to cause any force because the I component of the magnetic field is parallel to the current, and that part of it won't cause any force. So for me, force would be the I. For me, it was 18. The L for me was 2.5. And then I'm just going to multiply this by just the Y component of the magnetic field. Now, by the way, they're only asking for a magnitude, so I don't care about the negative sign here. So it's 90 milliteslas, which is 0.09 teslas. So 0.09. So that's going to be my force. For me, I get 4.05 newtons. Okay, but again, the key there is figuring out what's important. Well, I want to know what component of the magnetic field is perpendicular to the current. So I only focus on the J, or the J component of the magnetic field. Okay, so it looks like about half of you understood that. And then we have number 16. Oh, this was a toughie. Oh my gosh, only 4 of us got this right, and I think I know why. All right, so let me scroll over to that. 16, okay. So it gives you current in a circular loop, gives you a radius, gives you a magnetic field. And here's the key. It says the magnetic field is directed at an angle between the field and the plane of the loop and I think I left this 50 degrees for all of us. So these numbers might be different for you, but I think the angle was the same for all of us. Determine the magnitude of the torque exerted on the loop by the magnetic forces, answered blah, blah, blah. Okay, so first of all, I hope most of you know that we're going to use torque equals IA cross B, okay, which is IAB sine of theta. Okay, so most of you probably wrote that down and you're like, okay, I'm all good here. We know I, as given. A would be pi r squared, make sure r is in meters, and then B they gave you. The question is this. Okay, so let me draw this out carefully. Let's say here is your loop, okay? And the magnetic field, they say and I'm going to try to draw this as best I can. Here's your magnetic field. And they say the angle, this is where the careful part is, between the plane of the loop and the magnetic field is 50 degrees, okay? Well, in this equation, the angle that we need is, let's see, I'll use red here, the angle between the area vector and the magnetic field. So the blue lines here are the magnetic field, okay? So what is this angle here between the area vector and the magnetic field? Well, it's not 50. It's the complement of that. It's 40. So my guess is that most of you missed this because you should have put 40 degrees here, okay? So you just got to be real careful about what angle they give you in the description of it. It's they gave us the angle with respect to the plane of the loop. We need the angle with respect to the perpendicular of the loop, which is the complement of that. Okay, so that's my guess as to why most of you missed that. And then the last two, number 22. Okay. So in number 22, let me scroll down to that. Okay. They give you 2 long wires. They give you a separation. They say the current in one wire is twice that of the other, and they give you the force acting on 3 meters of either wire because they're going to exert the same force on each other. They're both going to either attract or repel with the same amount of force. They ask, what's the smaller of the 2 currents? Okay, so 31 of us got this right, so about half. But this one I was honestly expecting more. So here's your 2 wires. And just for the sake of argument, I'll say the current's going the same way. One of them is I, one of them is 2I. If they're going the same way, the equal force will be, they'll attract each other. All right, so the equation that you're using is force equals mu naught I1, I2, L over 2 pi R, okay? And we derive that in the notes, so if you need to look back at that, you can. But there's your force, okay? And then, and again, I'm going to do this all with variable form first. So mu naught I'll call I1 I, and I'll call the second one 2I. So one of them is half the other, or one of them is twice the other. And then L over 2 pi R. And then we're solving for I. So I times I is I squared. So I squared equals, okay, force times 2 pi R, okay, divided by 2. There's a 2 sitting here. And then our mu naught, and then L. Okay, so that's your equation for I squared. And that'll give you the smaller current. So if you square root that, you get I. And then, you might want to take some shortcuts here. So we square root this. There's a 2 here and a 2 here. I'll drop those. Mu naught is 4 pi e negative 7, and then there's a pi there, so I can immediately drop those. So this ends up being just F times R. Mu naught becomes just 4 e negative 7 when I divide, because the pi's drop out, and then your L. So that would be the equation like I would actually plug in my calculator. So they gave you the force. The radius is simply how far apart the two wires were. So like, for instance, in my question, that number was 8.1 millimeters, which I got to obviously make into meters. And then the L they gave us to, L was, for me, it was 3 meters. And my force was 85 millinewtons, so 0.085 newtons. So you plug and chug and you would get your answer there. So that's how you do that one. And then the last one that was missed frequently was number 25. 22 of us got that right, so a little over a third. So this was the second hardest question on the test. So let me scroll down that. And for 25, they give you a solenoid and then a wire that runs along the axis of the solenoid. So let me recreate that here. So here's the top view of your solenoid. So you're looking down into it. So like the magnetic field of the solenoid is going to either be into or out of the page. I'll draw into the page. So that would be like the magnetic field of the solenoid. Okay, I'll call that B1. That's going to be mu naught little ni for a solenoid. They give us n. Little n is, they give us turns per meter, 650 turns per meter. You might have a different number. The diameter is irrelevant. And then I, for me, was 280 milliamps, would be 0.28. Okay, so that's going to give you one magnetic field. And I'll plug those numbers in. So we got mu naught. For me, n was 650. And then I had a 0.280 for my current. And then they want this answer in microtesla. So I'm going to take whatever number I get here, I'm going to multiply it by 10 to the 6 to give me microtesla. And when I do that, I get basically 229 microtesla. Okay, so I get 229 times 10 to the negative something, and then when I multiply it by 10 to the 6 to get micro, I get this. Okay. Then they give us this wire. Okay, so there's a wire carrying a current. And that's going to make a magnetic field. Now, I'm assuming I'm draw the current coming out of the page toward us. That's going to make magnetic fields that circulate around that wire like so. I'm going to call that B2. So B2 is simply mu naught I over 2 pi R. For me, that current they gave me was, let me go look here. For that wire, they gave me a current of 11 amps. They said a point 2.1 centimeters from the wires. That's our radius in that equation. So for me, this would be 11 over 2 pi, and then my radius would be 0.021. Same thing here. I'm then going to multiply this by 10 to the 6 to get my microtesla. And when I do that, I get 105 microtesla. So I got my two magnetic fields. Now, what do I do with them to get the net magnetic field? Well, if you draw this out and look at a point, like let's say our point is, sorry about that. Let's say our point is here, and that's 2.1 centimeters from the wire. Okay, well, I got one magnetic field. At that point, the red magnetic field, and I'll redraw this here. So here's my point. Okay, so I got the red magnetic field at that moment pointing up. So that's our B2. And then our magnetic field of the solenoid, I got drawing into the page, that's B1. Well, how do I find the net magnetic field here of B2 and B1? Well, they're perpendicular to each other, so I have to Pythag. So I get 229 squared plus 105 squared, and then I've got to square root all that. Okay, so that is my net magnetic field. So it really helps to quickly sketch it out and look at the directions of the two magnetic fields. In this case, they're perpendicular to each other. Also, that question was near the end of the test, so my guess is some of you are also running out of time on that one too. All right, so I hope those were helpful, and if you have any other questions, obviously you're always welcome to ask me. Thank you very much.